Okay, great. Wonderful. All right. Well, thank you so much for the invitation to speak here today. So I'm going to talk about bulk reconstruction, in particular some non-perturbative aspects of it. And to do so, I'm going to describe the bulk in a framework that's appropriate to talk about non-perturbative things, even in the low energy effective description of the bulk, like the Hartle-Hawking or Wheeler de Witt wave function. So at the beginning, I'll review the general idea of bulk reconstruction, how we try to describe the bulk in ADS-CFT from boundary operators, and how there are some paradoxes which arise just from low energy reasoning, that is long wavelength reasoning in the bulk, but involve non-perturbative physics, in other words, not just in perturbation theory around the vacuum or a particular state. And so those things look like paradoxes. They seem to obstruct the mapping of bulk observables in terms of CFT observables. But then I'll try to convince you that if you describe the bulk physics in a framework that's maybe more appropriate to asking those kind of questions than just perturbation theory around some background, like the Hartle-Hawking wave function, these paradoxes go away, at least in the case of the eternal black hole, where we can really see how it works. And in some sense, the basic point is pretty simple, so I almost just say the whole thing on this one slide, but then I'll try to explain it in a way that will hopefully make more sense than just this one reading. So the idea is, does the information paradox or its various refinements actually obstruct the map between bulk operators and boundary operators? So in other words, if we study the low energy quantum gravity theory in ADS or in general, and we can talk about operators behind black hole horizons, and we think we know what is the description of those operators in perturbation theory around the black hole background. We think that that method will work around the vacuum, around any black hole microstate. That seems to give us some description of how those operators should behave, but then these paradoxes seem to contradict the existence of a CFT operator which has the same property. So for instance, just the black hole information paradox of Hawking would say that if you do that analysis, it seems to say that the evolution doesn't look unitary if I trace over the inside of the black hole, and that's obviously inconsistent with any CFT operator describing those observables. So another way of saying it is there really a linear map from what you would have thought in the bulk analysis is the entire bulk Hilbert space, the entire set of states described by the long-distance effective theory in the bulk into the exact CFT Hilbert space. Is there such a map, or is the range of validity of the bulk theory restricted, or is there something funny about the map? And I'll try to convince you that the answer actually is yes, which is maybe what we would have always thought anyway, but these paradoxes seem mysterious, and the point is that if you describe the bulk effective theory in terms of something like the Hartle-Hawking wave function, then it looks fully consistent with the CFT. Of course, the bulk wave functionals capture less of the full Hilbert space than the exact CFT. They only describe things which have no stringy or Planckian features in the bulk. But the particular bulk observables which seemed to break down, so we take some bulk observable and we try to find its CFT description, and very often it looks like the CFT description had to break down outside of some subspace, namely subspace of perturbation theory around the state we started with, some background state. That gets paralleled by a lack of invariance of the bulk observable under temporal diffeomorphisms beyond perturbation theory. So the bulk observable doesn't really make sense as a bulk observable either, so there's no discrepancy between the two sides. So you have to say something more to make this operator work, and if you say that more in the bulk, then it also works in the CFT. So that's the idea. Now, of course, we often have used ADS-CFT to describe or solve strongly interacting systems using classical gravity. The idea of bulk reconstruction is to go the other way. So we have an exactly defined quantum system, the CFT, and we should be able to use it to learn everything we wanted to know about quantum gravity. Of course, that's not so easy in practice. And obviously, one aspect is that gravity needs to be UV completed by string theory, but today I'm going to talk about some infrared issues, these paradoxes that arise when we consider states that are nonperturbatively different than the vacuum or than each other. And so what I mean by bulk reconstruction is what CFT operators correspond to bulk observables. And the best possible answer to this question would be if there was some general principle that selected what non-local operators in the CFT were special that should correspond to observations by local observables in the bulk. But we don't really know an answer to this question. We don't know what that principle is supposed to be because in gravity there aren't any local operators, so we're not going to find non-local operators in the CFT that obey some new exact locality, of course. So what is the thing at finite n? Maybe there isn't such a principle. Maybe this question doesn't make sense. But in any case, what is actually done under this name is to find expressions that have the correct large n limit around some particular state, like the vacuum or in other words, in the gravity language, in expansion around some particular background metric. Okay, so in the infinite n limit, there is an emergent exact bulk locality, and then these things have, that's what picks out these operators, but if you wanted to know at finite n what makes them special, maybe that question doesn't even make sense. Or, well, maybe it does and we don't know the answer. So there are two methods of reconstruction in this sense that I'll just briefly review. One of them we might call causal reconstruction. So the idea is in this subspace of perturbation theory around some background, which we might call the cold subspace. Then you can try to write the bulk operators in terms of CFT ones if you solve the bulk and perturbation theory and use the evolution equations to evolve the operators out to the boundary, and you get expressions like this, some smearing of a bulk operator, and you have to correct it order by order in the 1 over n expansion. And so this looks perhaps misleadingly simple because at higher orders you have to make lots of choices in this operator to account, to make it diffeomorphism invariant. And if we make different choices, you get different expressions here, and there isn't really a right choice, they're just different questions. And today I'm going to talk about some nonperturbative problem of a similar type where you have to make some extra choices that you maybe didn't expect. And then in another way of reconstructing bulk operators using boundary ones is to use the entanglement structure of the vacuum instead of the evolution equations. And that can allow one to write bulk operators in regions that you wouldn't have been able to using the causal reconstruction idea because they are behind causal horizons. So that could arise if I'm trying to describe the bulk using only a subregion of the boundary, and then you can actually reconstruct bulk operators in a larger region, the so-called entanglement wedge, rather than the smaller, only in the smaller causal wedge. And similarly, if I have a pure state of a black hole, some black hole microstate, you might ask, how do I try to write the bulk operators that look like they're behind the horizon? And these gentlemen showed that you can do that, again, in perturbation theory around that particular microstate. So we write some explicit expressions. And the basic idea of these entanglement constructions is that the Risch-Leiter theorem applied to the effective quantum field theory in the bulk tells us that you can get any state by acting on the vacuum or whatever your background state is with boundary operators, operators near the boundary. So that generates the whole Hilbert space, at least in the world of perturbation theory around a particular state. And so then if you also have the projector onto that state, the projection operator onto that state, I can construct any operator in perturbation theory by just summing up its matrix elements. Okay, so that's the idea of those reconstructions. But the paradoxes, like the information paradox and its refinements, are really not addressed directly by these bulk reconstruction if it is interpreted as a procedure that is only supposed to work in perturbation theory around a single state. So, the contradictions that arise have been sharpened, and these paradoxes, there's some incompatibility between, say, unitarity and the existence of the bulk operators behind the horizon described, if the bulk operators were described by the expected bulk low energy effective theory. Okay, so these are configurations that are non-perturbatively different from the vacuum, but we think they have low curvatures, so they should be described by the long wavelength effective theory, even though the total energy of the states is big, of course. And I sort of said this, so obviously so ADS CFT should tell us the answers, to these questions in principle, but if we don't know how to map the bulk questions to CFT questions, then we're not really sure what the answer is. And the whole point here is, whether the thing works on all states, which you would expect are described by the bulk low energy theory. Okay, so just to say it again, do we have a linear map like this? Or is it that the domain of validity of the bulk effective theory is smaller than you thought? There are firewalls. Or somehow the map is nonlinear, which might be suggested by state-dependent constructions of the operators, or ideas that entanglement of states in the CFT encodes gravitational observables, because entanglement isn't measured by a linear operator. Okay, and just to make a very simple point, this is kind of an aside, just to mention, of course, if we, by the RG flow here, I mean in the bulk perspective. So let's say we have exact theory in the bulk, and we know the Hilbert space, and we're interested in knowing the Hilbert space of a low energy effective theory. The relation is supposed to be a projection. So, of course, even in quantum field theory in general, Hilbert space isn't a tensor product of long and short distance modes. It's that there is a subspace of the Hilbert space described by the low energy effective theory in which short distance modes live in adiabatic vacuum determined by the long distance modes. So if you do RG kind of block transformation in Hilbert space, then on a 2 by 2 by 2 block, let's say in 3 spatial dimensions, I will get an n to the 8th dimensional Hilbert space if each lattice site has an n-dimensional one, and then I'm supposed to project it back onto an n-dimensional subspace. And of course, the standard way of doing that would be, in work of Kadanoff, let's say a long time ago, that would be a projection onto a subspace of something like the lowest total energy. So that will be finding the things which minimize the energy density. So that sounds natural. But a newer idea, which is extremely interesting, these mirror RG flow, interpreted as an RG flow on states, rather than a way of constructing a particular linear subspace, where you take a projection onto the maximally entangled subspace of the block. And so if I really applied that across the whole Hilbert space of states, it will be a nonlinear map. Of course, I don't think people who study condensed matter physics who use mirror think there's something nonlinear in the quantum mechanical description of observables in condensed matter systems. That's not how they use this. But if we really, well, we could contemplate that. So is that how it's supposed to work? And, well, today I'm going to try to tell you that the answer is no. It works in a much more conservative way. But that's what those paradoxes would have suggested. Either the bulk description breaks down, or there's something exotic about the mapping. Okay, so very similar paradoxes appear in the eternal black hole, so I'll just focus on that for simplicity. And so that's the thing that's described by the thermofield double state, and we heard about it already in several talks today. And then there's a version of these paradoxes there that was formulated some years ago. So the idea is very simple. So let's say I jump in from one side, from the right-hand side, and make some measurements. So I have some observable which is defined relationally to the right boundary. Well, clearly in factorized states, it should commute with everything on the left, because in a factorized state, the left system could be a thing I made up. They don't interact, they're not entangled, it has nothing to do with it, so it should commute. On the other hand, in the thermofield double state, we draw this connected Penrose diagram, and so I can meet this thing that comes in from the left, and so I can't commute with it. And that seems to contradict linearity. And just like in the information paradox, you might wonder whether exponentially small corrections to these operators could fix this problem. Although here that sounds strange, because in the unentangled states, it would seem weird even if there was an exponentially small commutator. But in any case, small corrections can't help, as shown by Papadopoulos and Raju. So the idea is that if there are not only this thermofield double state should be described by this Penrose diagram, but if I evolve in time, that just acts by some large diffeomorphism. I can think of it as a relabeling of the time axis on the left. Those will still be described by the same kind of geometries. I'll still should get the non-zero commutator. And there are just too many such states where the bulk description gives an answer that seems in tension. And so even if I allowed exponentially small corrections to those right-framed operator, it cannot fix the fact that I cannot get the answer I want in this kind of states and their time evolutions, as well as the factorized states. Okay, but actually an even simpler paradox, which is sometimes also referred to in the context of the ER equals ZPR correspondence, is just suppose I ask, what is the topology of space? Is it connected or not? What is the number of connected components of space? So in the factorized states, I would think the answer is 2, but in this Penrose diagram, the answer seems to be 1. And again, I cannot add exponentially small corrections to this operator C that will make it close to 1 here and close to 2 there, and work on the whole Hilbert space of what you would have thought is the bulk effective theory. So either it breaks down sooner, or something is funny with this operator. Okay, so that people have pointed out, and sometimes it's treated as there being a CFT problem with this operator. Clearly, there isn't such an operator in the CFT, but we sort of thought that it existed in the bulk theory, so there's something funny about the duality. Or there's something, this is a state-dependent operator. But what does that really mean? Okay, so I sort of said this. Of course, in perturbation theory around a given state with a semi-classical geometric dual, there's nothing to talk about because this operator is just a number. So obviously, we can write it as a CFT operator. It's trivial. It's the number 1 or the number 2. But the question is whether it extends to a sensible operator valid over the whole range of the bulk effective theory. Okay, I mean, another way of saying it, and just this is morally the same paradox as the information paradox. The point is that in all of these cases, the CFT states that are dual to what you thought were different configurations in the bulk have some small but not zero overlap, bigger than can be accommodated by consistency of the CFT. It's just a quantum mechanical system. So for instance, in the ordinary black hole case, the Hawking analysis assumes that there are the field operators behind the horizon consistent with the bulk physics, and there are just too many of them, so they will give me too many states to agree with the CFT analysis. Or similarly, in the eternal black hole, if you evolve by a long time, the overlaps between those states don't die off as coherent states after a long time. The overlaps saturate at some value, which is still exponentially small in n, but it's too big to... That's what tells you that you cannot have 1 over exponentially small corrections fix the problems with these operators. Okay, but actually the gravity description, at least in the Euclidean path integral, already knows about this overlap. So we're talking about, so one thing we could say, what is the essence of why something funny happened is the factorized vacuum had a non-zero overlap with a thermofield double state, whereas there's supposed to be, one is supposed to be described by this two disconnected vacuum, the other one is described by the connected wormhole geometry. So you might have thought, well, how could there be an overlap? But the gravity description sees that overlap. So here I produce the vacuum states by these two caps, and then the thermofield double state by this annulus. Here I just drew 2 + 1 gravity for simplicity so I could draw a picture. And then there's a nice Euclidean saddle that fills it in. Actually, it just looks like the empty ADS saddle. And so if I evaluate the on-shell action, well, I get the right answers. So it just looks like this combination, which is 1 over the square root of the thermal partition function. And that's what this overlap looks like. So the gravity path integral computes right in. So these two pictures are the same. I just drew the slice here in 2 different ways, and that will be important in a moment. Okay. Now, but in order to really see whether there was some tension with the bulk description, we should have described the bulk in a way which correctly took into account the constraints of diffeomorphism invariance nonperturbatively. So instead of describing the bulk by thinking about naive descriptions of diffeomorphism invariant operators, like, so the Marolf-Wall paradox is formulated in terms of things of the type, I pick a point on the right boundary, I follow a geodesic, transverse it by some distance, and measure some field there. And in classical gravity, that is nonperturbatively diffeomorphism invariant. It gives me some answer. But I'm going to try to convince you that there's something not right about this naive description of this operator even at the level of the Hartle-Hawking wave function. We need to refine the definition a little bit, and then the paradox goes away. You have to make some choice, and then you get different answers in different cases, but it's consistent. So, okay, so the bulk wave functional is just, okay, maybe this doesn't work anymore, but I'll just point maybe. So anyway, the bulk wave functional is analogous to describing weakly coupled quantum field theory in field basis. So you write a function of the fields. Of course, it only makes sense in perturbation theory, weak coupling. But that's all we care about in this discussion. But it's still non-perturbative in the sense that I can talk about states that are very different, non-perturbatively different from the vacuum, but they all have weak curvature and weak coupling. But in gravity, the big difference is that the analogous kets are labeled by metric on the slice, and there's no canonical time slicing, slice in different ways, and so the kets are not all linearly independent. I could formulate gauge theory in the same way, and I will have a wave functional of the gauge field on spatial slices, the spatial components of the gauge field, and again, they won't all be linearly independent. And that is how gauge invariance is encoded in this framework. Okay, so the matrix elements, so if I have a well-defined operator, and I compute its matrix element in terms of these ket states, they won't all be independent. They have to satisfy constraints. Okay, so we can think of doing some gravity path integral with the ADS boundary conditions and then fixing some metric on the time slice. And that's exactly how you define, say, the Hartle-Hawking path, the Hartle-Hawking wave function via some path integral. But here we ask for ADS asymptotics. And this path integral, we should think of evaluating it just in perturbation theory around the saddle. So that's enough for the purposes here. And then we can rephrase everything we know about the bulk physics in this language, but then the contradictions will go away. Oops. Okay, so in ADS, you have to have some ADS asymptotic form for the metric there, and so that's the only difference. And then, as I said, this defines a bunch of maps from the bulk Hilbert space into numbers, one for each intrinsic metric on the time slice that you choose. And so then I can think of that as defining some ket vector by using the inner product on this Hilbert space, if I knew that inner product. But they're not linearly independent, so I can compute the overlap between them. It's not zero. And infinitesimally, that is, if I look at two H's which are close to each other, it tells me that the wave function satisfies the differential equation, which is the Wheeler de Witt equation. So that's the, in the old, as shown by Hartle and Hawking a long time ago. But there are also non-perturbative overlaps, because if I take cats of different topologies, the overlap is still non-zero, but it's non-perturbative because there's some Euclidean saddle that connects them with some action. So it would be very hard to see that by integrating the Wheeler de Witt equation, because you'd have to evolve through some singular configuration where the bulk description breaks down when you try to change the topology of the slice. Let me skip this comment. Okay, so if we look at this picture again, we can interpret it in two different ways. We can think of it as the amplitude that the thermofield double state is factorized, if I make the two cuts here. But I could also think of it as the amplitude that the factorized vacuum is connected geometry, if I make the time cut there. But the point is, I'm not supposed to add this to that. These are just the same solution with different slicings. I could even draw them in these two ways, which is more suggestive. So now I'm just make the picture bent so I can draw the time slice as a plane. And we can see, so these are two things are identical. And what we say is the topology of space. So here we say that it's disconnected, and here we say it's the connected annulus. But just not the well-defined, oh yeah, I'm essentially done. So it's not well-defined because it depends on how you slice the path integral. And so it's not invariant under temporal diffeomorphisms non-perturbatively. It doesn't obey the non-perturbative piece of the Hamiltonian constraints. And so the operators C, the number of connected components of space, is just as bad as if I wrote down some operator acting on the Wheeler de Witt wave function which didn't commute with the Hamiltonian constraints. So we would just say it's not gauge invariant. And so there is no contradiction with the linearity of the map from the whole bulk Hilbert space of these wave functionals in the domain of validity of the low energy theory with exact CFT states. And in fact, you can say something similar about the more complicated observables. The more complicated observables that Marolf and Wald discussed, where I shoot the geodesic in from one boundary and measure an operator there, they also don't have a well-defined action on these states just by those words, because if you try to insert it into this path integral, it will not lie on the time slice, so it will, in general, not make sense. And you have to impose that it should lie on the time slice or gauge fix in some other way. And then if you do that, it eliminates the contradiction that you had before. Okay, so for instance, in one natural way of defining these operators, which fixes this non-perturbative lack of gauge invariance, they just don't look like pure right operators by definition, because they're required to lie on the time slice with the left boundary. So that's one way to do it. There are other ways of fixing the gauge non-perturbatively, and so they will agree or disagree with what you naively wanted on one or some other particular state, depending on the definition you pick. But whatever definition you pick, you get something that makes sense. So now there's no tension with the CFT. There, with some gauge ambiguity in defining these operators in the bulk, and if you fix it, you get things which look like perfectly mapped to perfectly linear CFT operators. It's just that the naive definition didn't work in the bulk either. I'll just skip that because I'm out of time. So just to summarize, it seems like the information paradox and its cousins and refinements would have implied a breakdown of bulk effective theory or some nonlinear relation between the Hilbert spaces. But the problematic operators, the operators that seem to not make sense outside of cold subspaces, don't make sense in the bulk theory non-perturbatively either, because they're not non-perturbatively diffeomorphism invariant. And if you change the definition so that they are, then the paradox also goes away. But I think it's an important and interesting question. What is actually the right framework to describe the outcomes of bulk measurements? Because if I fly into the bulk on a spaceship, I'm probably not going to measure this non-perturbatively gauge-fixed bulk non-local observable. Well, what exactly I am doing, I'm not sure. So I'll leave it at the end with that question. Right. Thanks very much.
Okay, so let me just double check. On you're not claiming that you cannot get a local operator in the bulk in a fully covariant way without specifying a slice, right?
Right. So I mean, well,
possible.
so suppose we look at this kind of operator, which is framed with respect to one of the boundaries. So we start with some point on the boundary, and we go along a geodesic by some distance and measure something. So in classical GR, that's a good operator. But actually don't know how to make sense of that in action on, say, these wave functions without specifying something more. So you would know how it acts on a wave function which was gauge fixed by saying that that geodesic had to lie in the time slice. But in the Wheeler de Witt wave function, you don't impose that condition. So you don't actually know how this operator acts on the Wheeler de Witt wave function. Or you might also say that this operator makes sense in insertion into a Euclidean path integral, but it's not clear. So, and normally, I mean, in local quantum field theory, insertions into a path integral always give us good operators on the Hilbert space because we slice the path integral into pieces. But that's the thing we don't know how to do here. So I think the operator which agrees with the insertion into the Euclidean path integral of the thing with the geodesic is the one where you gauge fix by requiring, you say that it acts on a set of kept states in which you only do the path integral over states in which that geodesic lies in the time slice. So that's perfectly fine, but then if you do that, it acts in a way that you didn't expect on other states. Also, when you say that in the context of this two-sided setup, it means that the operator is automatically not a pure right operator because the slice will connect the two sides if it's connected. So sort of by definition, it's not a pure right operator. I hope that answered the question.
Other questions? Yeah. Okay.
Sorry, so just to understand correctly, would you agree there's a well-defined classical function in the classical phase space, which would give you the C operator of yours? And the statement is that as a result of these non-perturbative constraints, that doesn't lift to a good linear operator in the quantum theory.
Right, good. So that's an interesting point. So I think the problem is that, right, so you might have said that there are two different things we might have meant by the bulk effective theory. One that we got by doing semi-classical quantization of the classical phase space, and the other one, the thing that Hartle-Hawking described by doing the path integrals that lead to that wave function, and they give different answers. But I think that's not precisely correct because the story about quantizing the classical phase space is somehow obstructed here because the classical solutions have singularities, so they exit the regime of validity of the low energy theory, and so you can't tell what the answer is by doing that kind of analysis. So I would say from that perspective, you will be agnostic about whether the operator makes sense. And then if you try to define things using the path integral, you learn that it has a non-perturbative ambiguity or obstruction.
Yeah, I agree with that. Just two short comments. I mean, one more obstruction to quantizing the classical phase space is this fat tail that exists in the gravitational classical phase space. I mean, it's the fat tail that exists in the overlap of states. It's the spectral form factor that people were speaking about previously. It's the fact that the overlap between these time deformed states doesn't go off to zero but saturates at something. But I just wanted to make yeah.
Right. But that's something that you saw from the CFT, let's say. But I guess the point I was trying to make is that if you define the states using this formalism, or using the bulk wave function or from the path integral, you would see something consistent with those fat tails. Yeah.
Other questions? All right, let's thank Daniel again.